In this week's exercise, we are going to combine what we have learned in the past 2 weeks and add a little more to find our first periodic orbit of the Solar System. The exercise starts very similar to the Poincare section exercise from the first week, but differently this time, we are going to start our trajectory close to the equilibrium, just as we did in the stability exercise of the last week, and run it for a long time so that it falls onto the strange attractor. The exercise starts very similar to the Poincare section exercise from the first week. But differently this time, we are going to start our trajectory close to the equilibrium, just as we did in the last week's stability exercise. After running a long trajectory, we are going to find its intersections with the Poincare section hyperplane, which we position such that it includes the z-axis and makes an angle theta with x-axis. Remember, these points organize on an almost one-dimensional looking curve. Let's say this is my Poincare section with its own coordinates yps and xps. My intersection points looked something like this. So the first thing which we're going to do new in this exercise is we're going to parameterize this curve according to the arc lengths on which the intersections are located. So let's say I have a interpolation curve like this, and since I start my trajectory near to an equilibrium, its zero is well defined, and then every intersection point on the Poincare section has their own arc lengths, which we can compute by calculating Euclidean distances from each other. So our interpolation function will be something like this. It will input an arc length, and it will return location of the point on the Poincare section. Next thing we're going to do is we're going to make a return map. Similar to what we did in the first week's exercise, but this time our return map is going to be a return map of arc lengths rather than radial distances. This way we will be guaranteed that we will have a one-to-one return map. This return map, shape of this return map is going to depend on where your Poincare section is located, but main features will be same among the different return maps, such as it will have a maximum and equilibrium will be located at its zero, and once the flow falls onto the strange attractor, it will never go back to the neighborhood of the equilibrium. Now, again, similar to what we did in the first week, we are going to find the fixed point of this return map by looking at its intersection with Sn equals to Sn plus 1 line. Then, let's call this point S fixed. we will input this point to our interpolation function to find its location on the Poincare section. And now we can back project this point onto the full state space, and then we'll have 3 coordinates for it, and this is going to be our candidate point for the shortest Poincare section, shortest periodic orbit of the Rosseler flow. But for a periodic orbit, this is not enough. We also need a period. In order to find a guess for the period, we are going to integrate this point such that it intersects the Poincare section one more time. And the time it takes for intersect again is going to be our guess for the period. We found a candidate point in the full state space and the candidate period for the periodic orbit. But this is not a perfect guess. So in order to improve this guess, we're going to use Newton method. In order to improve our guess for the periodic orbit, we are going to formulate the Newton method for finding periodic orbits. Our initial guess approximately will satisfy the periodic orbit condition. These t and x we guessed from the Poincare section and the return map. Now we're going to assume that the actual periodic orbit is close to x, and if we add some delta x to x, the periodic orbit condition would be satisfied exactly. But what is this delta x and delta t? In order to find them, we expand the right-hand side of this equation to the first order. And hope that this delta x and delta t are small so that the first order approximation is a good approximation. So the zeroth order term in the Taylor expansion of f of x plus delta x and t plus delta t is f of x and t plus partial derivatives with respect to x will give us the Jacobian of the flow. Plus partial derivative with respect to capital T will give us the velocity function evaluated at the final point of the trajectory. Now let's see where these two terms come from. We're going to start with variations due to delta x. So the variation in the ith element of the flow function with respect to variations in x is going to be its partial derivative of ith element of f with respect to jth element of state space vector times variation in the jth direction summed over j. But this partial derivative is precisely the definition of ijth element of the Jacobian, so we can write this variation compactly as a matrix product. Next term is a little bit more tricky. So the variations, variations due to variations in time again are going to be proportional to, of course, partial derivative of flow function with respect to capital T. But to understand what's this partial derivative, we need to look at the definition of the flow function, which was like this. Initial point plus the integral of velocity function along the trajectory. So in this definition, capital T appears only at the upper boundary of the integral. So the partial derivative with respect to capital T will be equal to integrand, which is the velocity function, evaluated at the final point. And of course, you need to multiply with the change in delta t. So this is where the second term comes from. Now, we're going to write this equation compactly in a matrix form such that on one side there will be errors and on the other side there will be our corrections. Now, we can rearrange the equation we just wrote down such that we have deltas, the corrections on one side, and the error of our initial guess on the other side. Remember, delta t was multiplied by the velocity function evaluated at the final point, and delta x is multiplied by Jacobian minus identity matrix. Now, before moving forward, we see that we have a problem here. We have d equations here where d is the dimension of our state space. But we have one more unknown than that, which is the time. And the situation is even worse. This matrix here has an eigenvalue 0. If the Jacobian actually corresponds to the Jacobian of a periodic orbit, because we know that for a periodic orbit, there is at least one marginal Floquet multiplier. So this matrix is not invertible. We're going to solve these problems at once by looking at the physical picture. In the Newton method, we are trying to refine our guess for an initial point and the initial period such that it satisfies the periodic orbit condition. But the periodic orbit in the state space is an orbit that closes onto itself. So suppose that we find a point on this orbit, we can still move along the orbit and the solution still is going to satisfy the periodic orbit condition. So in order to get rid of this situation, we need a constraint. We need a constraint such that we're going to look for only one of these points, not continuously many of them. A particular choice of a constraint, which we are going to do in our exercise, is demanding that the variations will stay on the Poincare section. Mathematically, we can express this situation by demanding that whatever variation we add to our initial guess, we want it to stay on the Poincare section. This means that it needs to be perpendicular to the normal vector that defines the Poincare section. So this tells us that don't look outside the section hyperplane. Now the next thing we're going to do is we're going to attach this constraint to the equations we have above and write the whole thing as a one matrix equation. So finally, we're going to write down everything we have in a single matrix equation. This matrix will act on our corrections, and on the right-hand side there will be our error. Elements of this big matrix are going to be like this. on the upper left corner, I'll have Jacobian minus identity. On the right of that, I'll have the velocity function evaluated at the final point of the trajectory. And below, I'll have the constraint, which is the dot product of Poincare section normal vector with the delta x. So let's look at the dimensions of these blocks. Here on the error, here I have a d-dimensional vector, and here I have 1 d0. Again, here the state space vector is d-dimensional. Below, the correction to the period is 1. Upper left block of our big matrix is a d by d matrix, because Jacobian is d by d and identity is a d by d identity. This block here, the velocity, is a d by 1 vector. Here I write explicitly number of rows and columns, because here I have a 1 by d vector in the transposed form, so that effectively what it does is it dot products with delta x and requires that to be 0 so that it will add our constraint to the problem. And this 0 is just 1 by 1. Now we have a matrix that is d plus 1 by d plus 1, which we just named with capital N, acting on the vector where we have our corrections to our initial guesses, which I just named capital D. And on the right hand side, I have another vector, again d plus 1 dimensional, which I just named capital E. Now, what we're going to do in our program is we're going to solve for D, now our big matrix is indeed invertible, and we're going to update our guesses and then iterate this procedure until we need the numerical tolerance we define on our error. Now you need everything you need to know to find your first periodic orbit.